Our next application is the handshakes problem. I mean, one of the things with that name. So back before Corona, there was a science conference, and scientists have met, where n is at least 2. Assume that, so some of them have exchanged handshakes. We make the following two assumptions. No pair of scientists have exchanged more than one handshake with each other, and no one shook their own hands. Claim there are 2 scientists that have shaken the same number of hands. So here is an example. If you have seen graphs, you will immediately recognize this as a graph theory problem, but it's not necessary to use that language here. So in this example, you have 6 scientists, and I'm drawing a line segment whenever 2 of them have exchanged a handshake. So A has exchanged handshakes with B and with C, B with C, A, and E, and so on. So here you see that A has exchanged 2 handshakes, C has exchanged 5, B has 3, D has 2, and F has 3. So in particular, A and D have exchanged the same number of handshakes. A couple words about why we need this assumption. They're actually both necessary. If you have a scientist who shook their own hands and you have another who didn't shake anyone's hands, then of course they have different numbers of handshakes. So you would get a counterexample for n equals 2. Likewise here, what can go wrong if there can be a pair with several handshakes is that you can have this. 3 scientists, one shook only one hand, one shook 2 hands, and one shook 3 hands because these 2 have shaken each other's hands twice. All right, how do you solve it? So let U be the set of the n scientists, and V be this set. These 2 sets have the same size, namely n. Now I define a map F from U to V that sends each scientist, let me call the scientist U, to the number of hands that U has shaken. I claim this is well defined because, of course, U has shaken at least 0 hands, and at most n-1 due to these 2 assumptions. This ensures that he has shaken at most 1 hand with anyone else, and this ensures that it's n-1, not n, because U itself is not an option. Now, let's look back at the pigeonhole principle. Ideally, we want to ensure that F cannot be injective. That would be our claim. Unfortunately, this is not the case. U is the same size as V, not bigger size. In other words, we have equally many pigeons and holes, so we cannot quite apply the pigeonhole principle. However, we have this here. So applying part C of the pigeonhole principle for injections, we thus conclude that if F is injective, then F is bijective. So to get anything out of it, let's assume, for the sake of, so let's just right away assume the contrary to get a contradiction. Then F is not injective. Sorry, F is injective, since we assumed that the claim is false. And therefore, using the pigeonhole principle, we conclude that F is bijective. Thus, F is surjective. Hence, there is a scientist A with F of A 0, because A 0 is in V. And there is a scientist B with f of b is n minus 1 because n minus 1 is in V. You can regard this as the extremal principle because A has shaken the least number of hands and B has shaken the most number of hands. But that's not, we don't need the extremal principle to do this. These are two elements of V, so we can, and the map is surjective, so it must take the value 0 somewhere and it must take the value n minus 1 somewhere. Next, this is a subtlety. People sometimes forget about it. We need to know that the scientists are different because their handshake behavior is different. Because n is at least 2, 0 is not n minus 1, so their f values are different, and therefore they're different. Now, have A and B shaken each other's hands? No, because f of A is 0. F of A is 0 says that A has shaken no hands at all. A has been socially distancing. In particular, he hasn't shaken B's hands. On the other hand, yes, because f of B is n minus 1. N minus 1, you can only get the value n minus 1 if you shake everybody else's hands, including A's. And this is a contradiction. You cannot have no and yes at the same time. This is a contradiction, so our claim is proved. So we applied the pigeonhole principle, but not we didn't immediately get the answer from it. We had to think a little bit further.